Welcome back, everyone. We're on to Test 5 material now. Test 5 is going to be November 6th. It's going to cover 3.5, 3.6, 3.7, and 3.8. Next week, we'll do the Test 6 material, and we will finish the material for the course. Okay. So Test 6 material will end the material, and then we'll have a week 7, to review everything from the course before you have to take the final. I wanted to make a note that I found a few exercises that were in the wrong section between 3.6 and 3.7, so I fixed them. I posted an updated version of the homework packet. Before you do the homework for these sections, make sure you update the packet. If you like having a printed copy, you only need to reprint the stuff from 3.6 and 3.7. All the rest of it's exactly the same. There have been, I think, 2 errors in the answers from exercises this semester from way earlier. Those are also fixed in the new version. This week, our theme is mostly going to be derivative shortcuts. Before I get into the derivative shortcuts, of which we'll learn a number, I wanted to talk a little bit about notation. So we currently have something like this, where we give a function a name, like f, and then we can write out, okay, this is what f is, and then we write as the derivative f prime and write what that is. This is a bit verbose, particularly if we want to write down a bunch of derivatives in a row. And so there is an alternate notation. And in this alternate notation, we don't bother giving the function a name. We just write this symbol at the front, the function we're taking the derivative of written out, and then what that derivative is. And so if you were to read this, this symbol should be read as the derivative of. And so every equation is a sentence. The sentence that this equation is the derivative of x squared is 2x. Our old notation still works just as well. We can use whichever one we want. But if we want to write something concisely where we're only interested in specifically the derivative of some function written as another function, we'll usually tend to use this notation. If we want to talk about the function in more detail, talk about the graph, talk about tangent lines, or evaluating the derivative, we'll tend to use this notation that we've been using so far. Okay, so first shortcut. The first shortcut is what is called the power rule. And the power rule tells you what happens if you take the derivative of a power of x. Now, we've taken the derivative of lots of powers of x before, but this rule is going to tell us how to take the derivative of any power of x. Namely, it's going to tell us that if you take the derivative of the nth power of x, you always get n times x to the n minus 1. Now, I've already kind of given you an example of that because we said at the beginning, if f of x is x squared, then f prime is 2x. That follows exactly this rule. But this also means that if f of x is x to the 5th, then f prime of x is 5x to the 4th. And as soon as you have completed test 4, you can use this rule anytime you're asked for a derivative of a power of x. You could take the derivative of x to the 10th in the way we have done before, where you would write this in as an x plus h to the 10th power minus x to the 10th divided by h, and then take a limit. But this would be a horrendous mess. And so what this rule does is it lets us skip all of this. Now, don't get too excited. We can't skip doing this all the time because this rule that we've just written down doesn't work for every function, or anywhere near every function. But it definitely works for x to the 10th. And so following this rule, we're going to learn that if you take the derivative of x to the 10th, then you are in fact always going to get 10 times x to the 9th. And note, this is not redefining a derivative or anything like this. This is telling you that had we done this in the way we did on the previous test material, then we would have gotten 10x to the 9th. Now, I want to note how useful this is, because even if we're given something like g of x is x to the 10th, find g prime of 2, we could, again, do this by calculating 2 plus h to the 10th power minus 2 to the 10th power divided by h, and then taking a limit, as we had done in the previous chapter. But we can now do something smarter than this. Namely, we can now say, okay, I know what g prime of x is. Namely, g prime of x is 10 times x to the 9th. This is just the same thing we wrote up here, but in this notation instead. And so that tells me what g prime of 2 is. It's 10 times 2 to the 9th, which is 10 times 512, which is 5,120. Now, I want to point out the power rule isn't just useful for things that are immediately given to you as powers of x, like x to the 10th. We talked a lot at the beginning of the class about how a lot of things that don't look like powers can really be written as powers. So, for example, when I take the derivative of 1 over x, well, 1 over x, remember, is the same thing as x to the minus 1. So this is actually asking me for the derivative of x to the minus 1. I did not say anywhere here that this n had to be positive, and in fact it doesn't. So I can use that exact rule, bring down the power, times x, and then subtract 1 from this power. So minus 1 becomes minus 2. Okay. And if you want, you can write this as minus 1 over x squared. Similarly, the square root of x is x to the 1/2 power. So when I go to take the derivative of this, the power rule tells me I bring down the 1/2 out front, and then I subtract 1 from the power. So 1/2 minus 1 is minus 1/2. And so if I write this down, this is 1 over 2 square root of x. Likewise, if I look here, this is x to the minus 3. And so when I go ahead and do this, by the power rule, this is going to be minus 3 times x to the minus 4. Pull down the power and then subtract 1 from the power. That's what the rule says. And so you could write this, if you wanted, as minus 3 over x to the 4th. Okay, now these first two, 1 over x and square root of x, these are actually functions that we use enough that I'm going to recommend that you add both of these to your shortcut list. Namely, if someone ever asks you what the derivative of 1 over x is, you can just say minus 1 over x squared. And if someone ever asks you what the derivative of square root of x is, you can just say the derivative of square root of x, it's 1 over twice the square root of x. Both 1 over x and square root of x are functions that come up often enough that it's worth having these in your back pocket so that you don't have to do the same derivative over and over and over again. I would not bother to remember the derivative of 1 over x cubed. If that comes up again, just do it this way like we just did. So we have one new shortcut, which we call the power rule, and then we have two more little consequences, the derivative of 1 over x and the derivative of square root of x. But we have more big shortcuts to use. So next up, I want to talk about what I'll call the sum rule. And this rule tells us what happens if you take the derivative of a sum of two things. Whatever those things are, I'm just going to call them capital A and capital B. The thing you get is you get the derivative of A plus the derivative of B. And if you want to write this in our other notation, you might write this as A prime plus B prime. Whichever of these ways you like. They're the same thing. I'll note right now, this works just as well with differences. So if I take the derivative of thing A minus thing B, then I get the derivative of thing A minus the derivative of thing B. So, in other words, derivatives work very nicely with sums and differences. Early warning, though, derivatives do not work nicely with products or quotients. And so we're going to have to talk about what happens when you have a derivative with products or quotients later. But for now, sums and differences, they work nicely. And so what does that give us? That means that now we can take the derivative of something like x to the fourth plus x squared, and the sum rule is going to tell us that when I take the derivative of x to the fourth plus x squared, I'm going to get the derivative of x to the fourth, which from the power rule, remember, is 4x cubed, plus the derivative of x squared, which from the power rule is 2x. Or 2x to the 1, it's the same thing. Or, similarly, if someone asked you for the derivative of the square root of x minus 1 over x, then we could use our formulas from before. The derivative of square root of x is 1 over 2 root x minus, and then the derivative of 1 over x, which is minus 1 over x squared, from, again, our shortcut before. And so here, you would get 1 over 2 root x plus 1 over x squared. That would be this derivative. Okay, so already we're handling some fairly complicated derivatives, especially if you think about how complicated doing these would have been back with our limit definition of derivative, but these types of derivatives we can now knock out right away. Next up, I want to talk about what happens with constants. And so here I'm going to warn you before I explicitly write out the rules that that's a constant. This is a constant. However, these are going to get handled very differently by the rules about constants. So really, there's two rules about constants. The first is, what happens if you take the derivative of a constant? Namely, if you take the derivative of a constant, then you always get 0. Now, this will make sense if you remember that the derivative is attempting to be a generalization of slopes. What do slopes do? Slopes measure change. And so really this is asking, okay, if I have a constant, how does it change? And, well, the thing that makes a constant constant is that it doesn't change. So this derivative is 0. So this should make some intuitive sense. And so that says this derivative up here, it was 0. Now, you might be inclined to apply this rule here to say, oh, the derivative of 7 is 0, and so this is just going to be 0, but it's not going to quite work that way, because this 7 is being multiplied by the x squared. And remember, I told you multiplication is a little more complicated than something like addition or subtraction. So when I go to handle this kind of situation, I'm going to have to use a slightly different rule. So here I'm going to tell you, if I have the derivative of a constant times thing A, what do I get? Well, I get the same constant times, and then the derivative of A, which if you want, you could write as it's the same constant times a prime, whichever of these you like better. So this is saying when I go to take the derivative of 7x squared, I'm supposed to hold on to the 7 and then multiply it by the derivative of x squared, which is 2x by the power rule. So really I broke this up. I have a 7 out front. I keep the 7. And then I multiply that by the derivative of x squared, which is 2x. And so ultimately, this is 14x. We're going to do a number of examples, but it's important to make sure you understand the distinction between this rule, where you just get 0, and this rule, where you keep the constant unchanged. So if we put all of our rules together, we can now actually handle something like this. And it's not even too bad. This first thing is going to be 4 times the derivative of x cubed, which by the power rule is 3x squared, minus 7 times the derivative of x squared, which is 2x, plus 21 times the derivative of x. Okay, x, note, is x to the first power, so this is 1 times x to the 0th. But this, and this is worth noting too, the derivative of x is just 1. Plus, and then the derivative of 2 cubed. Now, when you see a 2 cubed, there might be some temptation to think of this as, okay, well, I'm going to pull down the 3 and get 3 times 2 squared. But note, this has been written in a slightly tricksy way. Namely, this 2 cubed is just 8. And, well, 8 is a constant. And so by the first constant rule, its derivative is just 0. So if I tidy this all up, I'll get 12x squared minus 14x plus 21. And that will be my derivative. Okay, so that's all the rules for 3.5. There are going to be more rules in 3.6 and more rules in 3.7. But that's all of the rules for now. So I'm going to wrap this video up here. In the next video, I'm going to do a number more examples where we get to put all of these rules together and use them. I will note, the application of these rules is pretty mechanical, which is unlike almost everything we've done in this course up until this point. So you will have to practice with these to sort of refine the skill, but as you get used to it, it'll become sort of second nature to apply these rules. At least that's the hope. But that's all for now. I'll see you next time.